let's have a look at these mixing problems, and we'll look at an easier starting point where we've got the same input as output. So this is a mixing problem, but we have got the same input as output. So the example that I'm going to do, we start with a 1,000 litre tank, starts off with 15 kilograms of salt dissolved in 1,000 litres of water. If 10 litres per minute of pure water is getting pumped in to the tank, and 10 litres of the solution, a well-mixed solution, is going out of the tank, what we want to come up with is a formula for the amount of salt in the tank at any given time. Okay, so let's look at how we start this problem. And we look at the rate of change. So the rate of change of salt in the water, A is the amount of salt over time, that is going to be equal to the amount going in, or the concentration going in, times the flow. Okay, the concentration of liquid going in times the amount of water going in, and we're going to minus the concentration out again times the flow. Okay, now in this case, it's a fairly nice one, as I said before, because lots of things aren't too bad. So what have we got here? dA to T is going to be, well, the concentration going in is 0 amount of salt, or kilograms per litre. It's always nice to put the units in there. So that's the concentration going in, 0 kilograms per litre, times the flow, which is 10 litres per minute. And obviously here we know we've sort of got it right, because the litres cancel out and we've got kilograms per minute, amount per time. So kilograms per minute, amount per time. So we're sort of on the right track. Minus the concentration going out. Now, we don't know what concentration's in there. What is the amount in there at any given time? So this is A of T. That's the amount of salt. How much water is in it? It's 1,000 because it's not changing. Times the flow rate, which again is 10. And if we want, again, we can look at the amount is kilograms, how much salt is in it, over litres, times the flow rate, which is 10 litres per minute. And again, our litres cancel out and we've got kilograms per minute, which is exactly what we want here. The amount against the time, the amount versus time, amount versus time. So then we just got to simplify this as much as we can. This is dA to T equals, the nice thing is this is going to be 0 because it's pure water going in, so that's always nice, equals 0 minus A over 100. Now what we've got here is a fairly nice, simple, separable equation. So what I'm going to do to solve this is I'm going to take my A's over here. So we've got 1 over A dA equals minus 1 over 100 to T. So all I've done is separated all my A's to one side, separated all my T's to the other. In this case, there wasn't a T, which was nice. And we're going to then differentiate both sides, integrate both sides. So when we integrate both sides like that, what we're left with over here is log of A equals minus 1 over 100 T plus our C. Okay, and we could have some initial conditions here and things, but let's pretty this up the way we always do it. We're going to put everything to the power of E, and I'll do this slowly because Alan, we sometimes do this very, very quickly. E to the power of log A is going to equal e to the power of minus t over 100 plus c. Okay? So over this side, they just cancel out to get a. Now over here, we could write that as e to the power of minus t over 100 times some constant e to the power of c. Now, why do we put a times here? Because when we multiply these two things, we add the indices. Sometimes that's a case of, I know I didn't understand that at first. I was thinking, where did all this come from? But because we're adding the indices here, we're timesing down here, and we can let this just be another constant. So instead of calling it e to the power of c, we can call this d. So what we get is the amount equals d e to the over 100. And that's our formula. I'm pretty sure we've got some initial conditions. So let's go up here. What are our initial conditions? At t equals 0, a equals 15. We're told that from the question. We go back to the question. A $1,000 tank starts off with 15 kilograms of salt. So there's the initial condition. So at t equals 0, we know that a equals 15. So we know that 15 equals d e to the power of 0 over 100. Just wondering where we got that from, but that's okay. This is 1, so d equals 15. And what we end up with is, as our formula, is a equals 15 e to the minus t over 100. And there's our nice formula for the concentration of salt in the tank. Okay, thanks.